load path is simply the route that forces take as they move through a structure. In a steel connection, the load path describes how forces transfer from one component to another. For example, from a beam into bolts or welds, through the plates, and ultimately into the supporting member. Thinking about the load path helps engineers understand how the connection physically works. Understanding the load path is essential because every component along that path must have sufficient strength and stiffness. If the engineer misunderstands how forces move through the connection, it becomes easy to overlook a critical limit state or unintentionally overload a component. The load path also helps engineers interpret analysis results more intelligently. Analysis software can produce a tremendous amount of information, but the engineer still needs a mental model of how the connection should behave in order to judge whether the results are reasonable. If engineers do not fully understand the load path, they can miss important failure modes or make incorrect assumptions about force distribution. In traditional connection design, not understanding load path can lead to incorrect or missing calculations, potentially resulting in an unsafe structure. In design by inelastic analysis, not understanding the load path can lead to a garbage in, garbage out situation where the analysis model gives the results, but they're not physically meaningful, again, potentially resulting in unsafe connections. Examining the load path helps clarify that the primary purpose of a simple shear connection is to transfer shear force while allowing rotational flexibility at the beam end. By tracking the load path for a typical simple shear connection, engineers can see that the force primarily travels through the beam web, into the bolts or welds, and through plates to the supporting member. The beam flanges are intentionally not engaged as they would be in a moment connection, therefore blocking any potential load paths for the moment. The load path provides a roadmap for identifying possible failure modes. At every step in the path, engineers can ask, how is the force transferred here? What could fail? For example, if force transfers through bolts, the engineer must consider limit states like bolt shear, bearing, and tear out, maybe slip. If the force passes through a plate, yielding, rupture, or buckling may become important. Load path connects the physical behavior of the connection directly to the limit states that must be checked. The most important takeaway is that software results should always be interpreted through the lens of structural behavior. Engineers should not simply look for green check marks or pass-fail results. Instead, they should ask whether the stresses, deformations, and force flow make physical sense based on the expected load path. Advanced analysis is powerful, but engineering judgment remains essential. Understanding the load path allows engineers to distinguish between meaningful results and misleading ones. I want viewers to remember that even relatively simple connections, simple shear connections, have rich and important behavior. These connections are often treated as routine details, but they still involve complex interactions between bolts, welds, plates, stiffness, and deformations. By studying load paths and failure modes carefully, engineers can build an intuition that applies far beyond any single connection type. The goal of this lesson is not just to analyze one connection, but to help engineers develop a deeper understanding of how steel connections behave in general.